Okay, in 8.3b, you're just taking what we did in 8.3 with similar triangles and their relationships and applying them to some basic applications, practicing interpreting what a picture might look like, why it creates similar triangles, that sort of thing. So it says here at the top, calculating heights and or lengths of real-world objects can be a challenge, right? Objects that are heights greater than the length of your measuring tape or difficult to directly measure, such as distance across like water, right, can be estimated or calculated using similar triangles, right? So the goal today is to be able to, one, interpret the context of the situation and draw a model to represent that situation, and we're going to use similar triangles. Then find heights and or lengths using the proportions or your scale factor if you'd rather, and then interpreting your calculated results. So make sure that those results actually make sense. So here's a diagram that's already drawn for us. We're just going to label the parts. It says 2 trees cast shadows on the ground. The smaller tree is 17 meters high. The length of the taller tree's shadow is 15 meters, while the length of the smaller tree's shadow is 8 meters. Determine the height of the taller tree. So first thing, our goal is to make sense of our diagram. So the first information we were given is that the height of this small tree is 17 meters. And the length of the tall tree's shadow, so this length over here, is going to be 15 meters. And the length of the small tree's shadow, so over here, is 8 meters. Now the question is, why can we assume that these are similar triangles? Well, first of all, they're both vertical to the ground, so we're assuming this is a 90-degree angle. So we know that that angle is the same. Also, they should be getting their shadow from the same sun. So if these objects are close enough together, their shadow should be cast at the same angle. So if these two angles are the same, that third one's the same. So we can assume these are similar figures because all of their angles are congruent, which means their sides need to be proportional. So when we look at this, I could set up a proportionality statement, and you can do this one of two ways. If I want to find the height of this tree over here, I could say, well, this height should be to this height as this shadow would be to this shadow. So we could create a proportion h is to 17 as 15 is to 8. We then go ahead and solve that proportion. So 15 times 17 gives us 255. 8 times h, and we divide that by 8, and h is equal to 31.875, so about 31.9 meters. Okay. Now again, some people really like to do proportions relating the object to its own shadow, so you can do this as well. H is to 15, as this height of a tree would be to its shadow. It'll give you that same idea. So if I do h is to 15 as 17 is to 8, notice you still have 8h. 15 times 17, you'll get the exact same answer, so you can do it that way too. Okay, so once we know that, then again, goal 3 is to interpret your calculated results. So on your assignment, you'll be asked to state the result in a complete sentence. So we would say the taller tree is about 31.9 meters tall. Okay, so making sense of your problem, then solving it, and then making sense of your solution. Let's just do a couple more of these as we go. So Richard needs to know the distance across the pond. He measures the distances shown on the figure below, uses findings, determine the distance across the pond. So notice here we've got two similar figures. One is inside the other. So when we relate these ones, we need to be careful that we relate, right, this maybe to this side, as this short or longest side of the small triangle would be to the longest side of the large triangle. We can do it that way, or again, we can relate this short side to his long side, this short side to his long side. So maybe that would be an easier way to look at it. Let's do that way. So we do 20 meters is to 280. Yikes, 280. In the same way that this distance across the pond should be to its longest. Now notice this little 70 is only a piece of it. So the actual length of that full large triangle is 280 plus 70, or in other words, 350 meters. Once we have that, we just cross multiply. So we get 280d is equal to 7,000 divided by 280 as we solve. You can hear the buttons on my calculator. Awesome. 25 meters. So again, we make sense of it. This means that the pond is about 25 meters long based on his calculations, right? All right. Lastly, again, this is a triangle within a triangle. Your friend George is going to help you identify the height of the flagpole. George is 6 feet tall, and you note that his shadow is 10 feet long. At the same time, the shadow of the flagpole is casting a shadow 85 feet long. Thanks, George. Determine the height of the flagpole. So again, I'm going to put H right there for our flagpole. And this one already has measurements drawn. So again, we've got two similar triangles, this small one, and we've got the larger one. So we could say George is to his shadow as the flagpole would be to its shadow. So 6 is to 10 in the same way that the flagpole would be to its shadow. And then we go ahead and multiply. Multiply 10 times h, divide by 10, h is equal to 51. So in this case, again, we were finding the height of the flagpole. So the height of the flagpole is 51 feet. Okay. Again, making sense of what you're looking for and kind of the language related to it, always making sure that we are using full lengths, not just pieces of the figure, as we're practicing solving with our proportions.